So this is an extra set of notes that we did not do directly in class. Basically, we did a practice problem in class when we were working on worksheet 3.3. Anyways, so this is looking at two-dimensional motion when there is no gravity. Sometimes it's called relative motion. And so I want to remind you that 2D motion is where objects are moving in two directions simultaneously, horizontally and vertically, or in this boat, in the X and Y direction, where X is this direction horizontally on the page, and then this is up and down on the page. And there's a third dimension, a Z-axis, which we don't see, and that would be, in this example, something falling from the sky onto the water here, okay? So, but 2D motion just means moving horizontally and vertically or in two directions at the same time. All right, projectile motion is 2D motion, but now the object is moving through the air in free fall, which means we're ignoring air resistance. When we look at 2D motion, whether we're looking at an object moving in two dimensions on the ground or moving in two dimensions through the air, we must remember to consider horizontal and vertical motion separate from each other, independent. So now the most common kinds of problems are like boats in a river kind of problem. So we're going to do an example problem similar to what was on worksheet 3.3. So we want to assume we need to cross the river. So if the river is 100 meters wide and has negligible velocity, like maybe the water's not moving, how long will it take him to cross the river? So the river's width is 100 meters, and we're going to use distance equals velocity times time, which is what we learned in Unit 1. Then we're just going to solve for time and plug in the 100 meters and 10 meters per second, and so that's 10 seconds. So he kayaks in this direction across the river. He's going to have to go 100 meters. He's going 10 meters per second. It'll take him 10 seconds to go across the river. 10 seconds. Now let's assume the river is flowing now. And so now the person is going to row their kayak in this direction along the red arrow. But the river is moving in this direction, the longer red arrow, at 20 meters per second. How long is it going to take him to cross the river? Again, we're treating direction in a motion in each direction independently of each other. They happen simultaneously. He moves horizontally and vertically at the same time. So the time moving horizontal and the time moving vertical are the same. However, or our time across the river and the time moving downriver is the same. However, we're only going to look at the going across the river. So horizontal and vertical motion are independent of each other. So again, we're going to use distance equals velocity times time. We put in 100 meters. It's still, even if the river is pulling him down, it's still only going to take him 10 seconds to cross the river because he's only vertically traveling that same 100-meter distance. Okay, so it's still 10 seconds. But his resulting displacement and his resulting velocity will follow this yellow arrow. So what it's really going to ask is how far downstream does he end? Then I would only look at the horizontal velocity and that time of 10 seconds. So then this was distance equal velocity times time. It's the 20 meters per second, and now he's moving horizontally for 10 seconds. And so that's why even though the guy is kayaking across the river in this direction, up, he gets displaced to the right 200 meters because he was also, while he was moving up, his boat was actually moving in this direction. So he crosses the river in 10 seconds, but he ends up 200 meters away from his final destination he was shooting for. All right? So that is how you work through two-dimensional problems there. Okay, so now there's this really good video that Ant goes over it, and so I'm going to play it for you.
It's a beautiful day, so let's take a break from physics and go for a paddle in the river. Here's a view of the river from above. And let's say we can paddle at 2 meters per second in any direction we like. But to make things interesting, let's have that river start moving with a current of 1 meter per second to the west. So you probably know that if I paddle in the same direction as the river, my overall or resultant velocity will be 3 meters per second. And if I paddle in the opposite direction of the river, my resultant will be only 1 meter per second. So I guess I go faster when the river is with me and slower when I'm against it. Now that makes sense. Now let's say I want to get from point A on the southern bank of this river to point B on the northern bank. So what's going to happen when we aim our canoe north towards point B? Well, the velocity of the river current is going to push us off course, and we won't go exactly north. We'll go north and a little bit west. We can see our overall velocity, what we call our resultant velocity, by drawing a proper vector diagram. We'll draw the velocity of the canoe and the velocity of the river as the components, so they'll go tip to tail. And we'll draw the resultant velocity in the direction that we'll actually go, tip to tip and tail to the components. We can even work out how fast we'll be moving. We can use the Pythagorean formula to get the magnitude of the resultant, which works out to 2.2 meters per second, and the inverse tan ratio to get the angle, which will be 27 degrees west of north. So how far downriver did we end up? For this, we need the width of the river. Let's say it takes 10 meters to travel from point A to point B. We can add that vertical, or y displacement vector, to our diagram. Here's the vector that represents the displacement of the canoe going downstream, the horizontal, or x displacement. So how are we going to figure that dx out? Well, we can model the motion of the canoe with a uniform motion formula, v equals d over t. This makes sense since the canoe is not accelerating while it's in the river. Substituting into this formula is a lot trickier, though. We can put in 10 meters for the displacement, I guess, but what velocity should go in? There are 3 different choices here. There's a key idea here that helps you work this out. When you're working with kinematics formulas, you need to substitute in x vectors with other x vectors and y vectors with other y vectors. Or, as I often say in class, keep your x with your x and your y with your y. This means that if you substitute in a y displacement, like 10 meters, you have to also sub in a y velocity, in this case 2 meters per second. That will allow us to calculate a time of 5 seconds, which is how long the canoe is in the water for. After we know the time, we can do a second uniform motion calculation for the x direction. This time, we'll use the x velocity of 1 meter per second along with the time to get the x displacement of 5 meters. Lastly, what if we wanted to go from point A to point B exactly without drifting any? How could we make that happen? Well, we would need to paddle our canoe into the current, actually aim ourselves a bit to the east to counteract the motion of the water moving to the west. We can draw that out with another vector diagram. This time the velocity of the canoe is the diagonal vector and is aimed a bit to the east into the current. These 2 vectors are still components, and they're still tip to tail, even though it's kind of weird that the green canoe velocity component ends up being the diagonal. The resultant, our overall direction of motion, will still be tip to tip and tail to tail with the other 2 components, and will point straight north. Note this is an example of a resultant not being the hypotenuse of the triangle. We can even calculate the magnitude and direction of this resultant. Just be careful when you use the Pythagorean formula that you make side C the hypotenuse of the triangle, 2 meters per second, and then solve for either side A or B, which is the resultant.
All right, there you go. If you need help, please come to tutorial and ask for help. There will also be extra practice problems online.